That little orange box in your kitchen? It's hiding something. Most people walk right past it every morning without a second thought. This ordinary white powder can bake muffins, kill odors, and stop grease fires. Think about it. One substance, three completely different jobs. That's like one key opening your front door, your car, and your office. In most American kitchens, baking soda just sits on the shelf, never causing trouble, never asking questions, waiting for something to happen. But here's what doesn't add up. The powder in your pancake batter is the same one, scrubbing grime off your stovetop. That's strange. Dig deeper, and it gets stranger. Baking soda appears in toothpaste, fire extinguishers, pool chemicals, and heartburn pills. Same thing. Every time. So the real question isn't what baking soda does. The real question is, why does one simple compound do all of this? But look closer, and something doesn't match. It reacts with acids, yes, but why doesn't it react with everything it touches? Calling it a simple powder might be the first mistake. Nothing it does is simple. Is this pattern expected, or just familiar? Let's start in the oven. Mix baking soda into banana bread. Batter with buttermilk. Watch what immediately starts happening inside that bowl. Baking soda hits the acid in buttermilk and releases carbon dioxide. Bubbles trapped in the batter like air pockets in a sponge. Heat expands the bubbles, dough pushes up, and your bread turns light and airy. No baking soda? You get a flat, bitter brick. Now, the fridge. Leftover salmon from Tuesday? By Thursday, it's not just unpleasant, it's a chemical problem. But baking soda handles that. Most food odors are acidic molecules in the air. Baking soda, being alkaline, neutralizes them on contact. It disarms, not just masks. Third situation, your cast iron skillet after Sunday breakfast. Burnt eggs, stubborn grease. Sprinkle baking soda on the pan and start scrubbing. No acid this time. Crystals act as a mild abrasive, rated 2.5 on the Mohs scale. Tough enough to clean, not scratch. 3 different situations. 3 different mechanisms. One box handles all of them. That pattern is far too consistent to ever be a coincidence. This pattern is too consistent to ignore. Baking soda doesn't do different things. It does one thing. Expressed differently based on context. But wait. If that's true, why doesn't it react with the cardboard box around it? What assumption are we actually making here? Let's talk chemistry. No textbook required. Baking soda is sodium bicarbonate. 1 sodium atom, 1 hydrogen, 1 carbon, 3 oxygens. Formula: NaHCO-3. Its pH in water, about 8.3, mildly alkaline. Lemon juice is 2, water 7, bleach 13. Baking soda sits in the middle. Most people don't know. Baking soda isn't mined. It's made via the Solvay process. Salt and limestone combined to form sodium bicarbonate. Key principle: baking soda is a chemical buffer. Think of a train's shock absorbers. They don't stop motion, they smooth it out. When baking soda meets an acid, it neutralizes it. In a basic environment, it resists. No overreaction, just balance, restored every time. But pH only describes baking soda dissolved in water, not its dry crystal form, and not every complex real-world situation it faces. Take a grease fire. Baking soda smothers it with carbon dioxide, cutting off oxygen. A completely different mechanism, same powder, different physics. This is where it gets hard. Chemistry is clear. But no model explains why one compound handles fire, fermentation, and your fridge. Here's the surprising part. Different fields describe baking soda completely differently. Food scientists focus on CO2, chemists on neutralization, engineers on abrasion. Each model is correct. Each is also incomplete. No single explanation covers all observed behavior. That's not a flaw. It's a clue. Model 1. The activator. Baking soda does nothing until acid arrives. Acid is the trigger. Soda is the spring awaiting release. This explains why baking soda without acid gives flat, bitter results. The reaction never fires. The spring stays loaded. Nothing rises. Nothing transforms. Model 2. The neutralizer. In your fridge, on carpet, in shoes, baking soda triggers nothing. It absorbs imbalance and quietly restores equilibrium. Unlike baking powder, which has a built-in acid and self-activates with moisture, baking soda in neutralizer mode depends entirely on its environment. Both models capture something real. The activator explains baking. The neutralizer covers odors and cleaning. Together, they explain roughly 90% of it. But neither model explains fire suppression, and neither explains why baking soda stays stable for years, then instantly activates when conditions shift. Here's where it gets strange. Neither explanation fully resolves the pattern. The soda in your pantry right now isn't passive, it's waiting. That box sits there, not reacting, not degrading, nothing visible. Add lemon juice, heat, or an odor molecule. It responds. Instantly. Back to the shelf. In 1846, bakers John Dwight and Austin Church began selling sodium bicarbonate. That company became Arm and Hammer. And long before that, ancient Egyptians used natron, a natural sodium compound from dry lake beds, for cleaning, preserving food, and mummification. That orange box is not just an ingredient, it's history, a balancing tool, and proof that useful things never need to advertise. At Amazing Nearby, we find what hides in plain sight. If that's your kind of thing, you already know what to do.